Okay.
Sorry, how does the study session work?
So basically, if you have any questions, I'll try to, when there's something really hard in a few lectures, or like a concept that's hard to understand in a few lectures, or that's not explained good, I'll try to explain better. But if everybody understands everything, we can go over the homework or any questions that you have. In the future, when we come up to magnitudes and all that, I'll try to bring harder questions if someone wants. But right now, I don't really have any harder questions because there's not really much to it. I mean, every possible question on Gaussian surfaces has been asked in the homework.
Yeah.
First question. So if you have a positive charge and then a charge 2 times that, is there any way you can bring in a third charge and put it in a place where the potential or the voltage will be the same?
The voltage will be the same as before.
As before, okay. No, it's negative.
Negative. 2 kilo.
Also, what's the equation for voltage?
For voltage or for energy?
Voltage.
Voltage. Do you even go over voltage?
I don't know. I just want to know.
We
kilo.
did.
We did potential energy.
Oh, we didn't?
I don't think it did voltage yet.
No, we didn't.
What's potential energy?
Potential energy is KQ over R. So you want to bring in another charge, positive or negative?
Either.
And make the potential the same.
Voltage, actually, I guess this
Potential energy. I mean,
this was a question from the voltage checkpoint.
Voltage is voltage is defined at either a point or at 2 points. It's not defined in the system.
Oh, it isn't?
No. So you can't say that the potential of the system is this much. You can say potential energy of the system is this much. So if you want to, you can bring in one if you want for the. Today they asked the question in class for something similar to this actually. I think it was.
Wasn't it the plates where if they have a Q charge? Is that what you're talking about? Plus minus if it was minus minus.
Yeah.
Yeah. That
There's something similar to that. Yeah. That question. I think that was a checkpoint question. So it might be the same one you're asking about.
You did the checkpoint for that already?
Potential energy.
Yeah, I'm checking.
Oh, this one. We haven't covered it yet. But
This one is for potential or potential? Yeah, potential.
electric.
Potential. Yeah, potential.
Electric potential.
The potential in a certain region is going to be the following graph. Okay. At which point the magnitude of the EP will be greatest?
Would it be Q?
I think so.
Because that's where the voltage would be like really, really high, right?
Mm-hmm.
Oh, it is. It was potential, electric potential.
Energy. Is potential energy? Electric potential energy. So yeah, you can. So if you bring right now the energy of the system is K Q R. So if you bring in another charge at any point, positive or negative, the
You'll have 2 more terms.
yes, it's going to be K Q the third term is going to be k q1 q3 over r plus k q2 q3 over r. These two have to add up to 0 to cancel out. So that means the r's.
One of them is going to be negative for sure.
Yeah, one of them is going to be negative because positive and negative. So if this is positive, it's going to be positive, positive. This is negative, positive, negative. And depending on, so since this is bigger, it's going to be further away from that, closer to this. So it should be the same thing. That's like, it's like the same thing, kind of same thing as the first question, which is where the electric field is 0. Where the electric field is 0 on the line. No, back in the first one with problems. So you just have to find which distance satisfies this equation. Okay, Q1, Q3 over R1 equals K, Q2 over R2. K's can cancel out, and here we're talking about magnitudes.
I did that one.
What? Did you get it? Yeah, I got it.
Do you have any questions on that?
I have a question about the previous homework. Do we do that or no?
No, that's fine.
You sure?
Yeah, that's fine.
Awesome. I couldn't do it.
And
I couldn't do
This is the
it.
first one, the sphere one.
The previous one. The last homework that was due.
Right, I'm on it. Is it the sphere one? Yeah.
Yeah. Did you guys do that last time? Or
we did some of them on Friday. I don't remember which ones.
Just talked. No one else was here.
really?
This is
A and it's 0.4? 0.04 meters. And B 0.06.
This is B, right?
Yeah.
Does the shell have thickness? Can I see actually?
No, it's
okay,
just
okay. It's
yeah.
shell. So this is B.
And then P
0.06.
Yeah.
Okay. What's the charge?
Plus 9 microcoulomb.
Okay. And they want.
And then P, there's a P at -5 along the y-axis. Along the y.
On the y-axis. So this is, let's call this D.
And that's 5 centimeters.
0.05. And this is P. So they want the electric field here, right?
Yeah.
What do you do? What did you do?
What did I do? I wrote a bunch of them. Wanna see?
Mm.
Okay, I use E, Q, K, R, da 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 da. This?
Didn't use Kiss as well.
Oh, that's it.
Gauss
I
as
think
well.
I did, but it still did
Did you
not
pick
give
your
me.
Gauss insert? So any look all the equations for electric fields like KQQ over R squared or 2 lambda K over R, all those are derived from Gauss's law. So any electric field problem, if you start it by Gauss's law, you're going to get to the right answer if you do it right.
Okay.
So Here, you can also start with Gauss's law. When you pick a Gaussian surface, and for Gauss's law, just
ETA.
right? This says that around this closed surface, which is Gaussian surface, a Gaussian surface, a Gaussian surface. So you have to pick a Gaussian surface around the place where you're calculating the electric field. And preferably, it has to be symmetrical because that way you can get rid of the integration. Otherwise, it's not going to work out. So if you pick,
But then here in the middle, there's nothing, right?
There's
so you
nothing in the
subtract
middle.
that.
But you want to calculate the point at this point. And when it says E dot dA, what does this mean, E dot dA? This means if you have a surface with charge in it, let's call this Q enclosed, the electric fields so the integration of the electric field dot the area, which is the area of this surface, is equal to Q enclosed over epsilon naught. So this says that the electric field at this surface. Electric field at this surface. This doesn't talk about the electric field inside.
Okay.
It only mentions the charge inside. So the electric field at the surface. So you want to use a Gaussian surface at the point where you want to find the electric field, because it's only talking about the electric field at the surface. So that's why you pick your Gaussian surface at point P. So the surface is at P. Right? So it's a sphere. On the surface of that sphere, there's a point P, and it's centered right here, same as all the other stuff. Same as the same center with these two, or with this one shell. Right. So I'm going to do. I'm just erasing this with my hand. So E dot. Epsilon naught. All you have to do is find Q enclosed. Now, it says the integral, right? And for you to get rid of the integral, there has to be two
things have to
two
be
things
true.
have to be true. Yeah. One of them is that the electric field must be perpendicular to the surface, right? That way you can get rid of the dot product, because A is defined as perpendicular to the surface. So two vectors parallel to each other.
Yeah.
That's the same thing as E times A. The same thing is that E has to be uniform throughout the entire surface. That's why you need symmetry in these kind of problems. So if a point was here, you can't pick a Gaussian surface here, because the electric field here is going to be stronger than here.
Yeah.
So that point has to be here. Like this. It has to be here. So that the same electric field is throughout the surface is equal. So in that case, you can get rid of the integral and write this as E times A equals over epsilon naught. Because we have symmetry, and because when we have symmetry, usually you can get rid of the two. I mean, the two conditions are always true. We have symmetry.
dA. The dA is a vector, right? Or is
dA is a vector.
And it points normal to the surface.
So E equals Q enclosed over A and epsilon naught. A
That's like 2kq over r, kind of, right?
kinda. You want to make it into that form, into a form like that. You're gonna make that by finding the area and finding Q enclosed. The area is the area of the Gaussian surface, as we just said, because that's what the Gaussian law tells us. The area of the Gaussian surface you just chose. So you chose a Gaussian surface with radius equals d, right? Remember?
Yeah.
So the area of this Gaussian surface is what's the surface area of a sphere? Let's just call it b squared for now. 4 pi d squared. D squared. Sorry. It's this d. Right. This is our sphere here. That's a sphere. Surface area is 4 pi d squared. And we just have to find Q enclosed. How do you find
That's
Q?
density V, right?
Huh?
Density times volume.
The density, yeah, the density times the volume. So rho times V equals Q enclosed. What's rho? And what's V?
Rho is 9 microcoulomb.
Isn't it Q? Q is distributed throughout this entire thing. Fine.
Oh, okay. I found that actually.
Mhm.
Q.
Mhm.
Q over V,
Yeah, which V?
volume of the sphere.
Which sphere?
The sphere at P.
Why? It tells you that Q is distributed uniformly throughout this shell. So when you're talking about
Oh, it would be from A to B.
the volume from A to B.
That's what I did actually.
Q.
I just didn't know how I did it.
Right. So we can just write it down.
It's 9 over 4 over 3 pi. 4 over 3 pi. BQ minus.
Okay. So that's equal to your rho. Now your other V. What's your other V?
What other V?
We said Q enclosed is the volume times rho. Rho is equal to big Q over big V, which is the outer area. Why do we use
That, okay, that V would be, go ahead.
Hmm?
Go ahead.
What do you want to say?
I was gonna assume what the V was.
Why do we use rho in problems like this? Rho for when it tells you the charge is distributed uniformly throughout something, either throughout the area, throughout the length of the wire, throughout the area of a sheet, or throughout the volume of the
It's
object.
throughout the whole thing.
Well, the entire thing is
Yeah.
distributed uniformly. That means rho is constant. So if you take the entire charge of the entire body, you can say the entire charge over the entire body, which in this case is BAV, is equal to a smaller charge in a smaller body. That's why we use rho, because it's constant. So if we pick a volume here, Q over V is going to be same as this entire Q over this entire V. Right? So
Our job is to find that little Q.
yeah, so all we have to do is find, what we want is find this little Q, which is Q enclosed. In this case, this is Q enclosed over small v, which is this small v here. This is the volume of the spherical shell that's enclosed. And how do we find that?
I got a number for that. So I was correct up until that point.
Okay. So Q equals, you can always, you don't have, if you don't like start doing this way with rho, you can always just write out rho equals big Q, big V, which is equal to small q, small v. So Q enclosed is equal to small v times big Q over big V, which we just over 3 pi BQ minus a cubed.
Isn't that R cubed instead of B?
Yeah, R cubed, but I'm just still using the same things they gave us, which is A and B. That's what we do sometimes. It's big. It's the big volume, the volume of the big sphere minus the volume of the small sphere. The big sphere has a radius of B. And the small sphere has a radius of A because we want this volume.
No. Because to find the volume we do from A to B, right?
The volume.
I'm sorry,
of the sphere.
the volume of the sphere.
Yeah, the volume of the sphere. What is it? The spherical shell, not sphere itself.
The spherical.
The spherical shell, right?
Yeah.
What's the volume of the spherical shell? This spherical shell.
It would be from A to B.
The volume, what is in here from A to B? How do you find that? Volume of B minus volume of A.
Yeah.
You're left out with what's
Yeah.
outside, which is the same as, so volume of B minus volume of A equals 4 over 3 pi B cubed minus 4 over 3 pi A cubed. Factor out 4 over 3 pi.
So that's just the volume for that spherical shell.
Just this spherical shell.
But the V for the Q enclosed should be different. It should be from.
Yeah.
Yeah,
He hasn't brought it over yet. That's for the big cube. That's for the
Oh.
total.
Times is, yeah, times is small b.
okay, sorry.
So what's a small b? 4 over 3 pi.
Times r cubed, or no, wait. Whatever, 0.05. I don't know.
Yeah.
What is
D
I called
cubed
it
minus
D
A
cubed.
b cubed minus a cubed.
Is this smart physics too?
Huh? No, I don't think so. It's just old smart word. That's smart. So yeah, we ended up with this term for q enclosed, right? We can simplify yeah, 3 pi, so that leaves us with q equals q enclosed. Q equals is equal to q, which is a q, times g cubed minus a cubed over b cubed minus a cubed. That's your q equals. And this is our equation. I should plug in stuff. So E equals q equals b cubed minus a cubed over b cubed minus a cubed. That's q equals, and we have a equals 4 pi p squared. 4 pi p squared. And we have epsilon naught left over. So epsilon naught.
I got this right up until Q enclosed, and then I did a bunch of math and I gave up.
Wait, until when?
I got it up until here, Q enclosed.
Q enclosed.
Which
Yeah.
I had that, and then I switched to like 2K enclosed R, and
Okay.
I couldn't do anything.
Okay. Or just continue doing it the same way. I mean, using numbers, I usually don't like using numbers instead of, I only like using numbers at the last step. You simplify everything to variables and all that. And then, especially with smart physics, because it states like A equals this much, B equals this much. So if you write everything in terms of A and B and C and everything they give you,
Plug
you end
it
up,
in.
and you plug it in and it gives you an easy answer.
Thank you.
This is what I got.
What'd you get?
1, 2,
990791. Except it's negative. Hey, doesn't tell me actual value. Are you from graded? Yeah.
What?
Why doesn't it tell me the actual value?
I don't know. I don't work for smart physics.
Because I think I didn't use very close numbers. How does it calculate that you're close enough?
It has, I think, a 3%.
What?
3%.
So,
3%.
if you have a really big number, like 5 million,
Yeah.
you have 3% margin for error. But if you have a really small number, like 0.0000,
It's the same thing because you can express them all as scientific equation. So it's going to be 5.0. No, that's not.
right? Don't, yes. How about this last? I don't remember.
Fine.
What?
What do you say?
I haven't done any of the homework for 5.
For 5, okay. Thanks, that's for fun.
Oh, there's only one problem for 5. Is that because 4 was so much? Or is this just really long?
No, there's not really much. I don't know. Hey, usually potential energy constants are all the same thing. The potential energy of the system, or
KQQ.
what's the potential energy at this point, or something, or what's the potential energy of the body here, or something.
How did we get to KQQ? Is that
Work, integral work.
negative? Isn't it?
The U is a
Negative
integral work from point to another point.
So then you just raise it to the R, and you get 2, but this is negative, right? Okay, got it.
And potential is U over Q times U over Q.
Voltage. Why don't you like to say?
Let's say called potential.
Do they?
Yeah, it's called potential, and later on in circuits, when it gets to when it gets to the circuits part, it starts calling it voltage.
I like calling it voltage.
It doesn't sound right when you're working with a system.
What's the voltage of the system?
What's the voltage of this? I mean, not of the system. I mean, with particles, like a charge, like 2-point charge. It doesn't sound right.
So
It's
how do you calculate the voltage in the system?
You don't have voltage.
You don't?
No, at a point. A point or
So it's, you only look at one particle and then you look up. I mean,
the voltage is a state, is a property of a place, of an area, of a spot.
So like,
Or-
one started and one there. What do you mean?
So,
Yeah, explain concepts.
so this is Q plus, right?
Okay.
Actually, this is extremely like, I'm going to do another thing here. This is also Q plus, right?
Mhm.
We first started out by saying, if you have, let's say this is equal to 70 microcoulombs, and this is also equal to 70 microcoulombs. So let's assume that this is equal to 3 microcoulombs. And this is also equal to 3. I'm not going to keep on using equal to. Equals 3 microcoulombs, right? First started out by saying the force between those is F and F, right?
Mhm.
Right? And then, so this is the same as saying that the energy of the system equals U equals something, right? And then we wanted to define the force, the same thing. We wanted to define the force as a property of the place, the area. So we divided it over Q and got the electric field. So the electric field at this point, right?
Mhm.
Electric field at this point
Mhm.
is this much and this much, right?
Mhm.
This is the same thing. We took out the point and said the potential at this point is this much and this much. It's the same thing from another charge. It's also from another charge. We just took U, that's P equals U over Q. Here, E equals F over Q. So they defined the electric field as the electric force that affects a point charge in this point, right? It's basically what a field that affects a point charge, because it's a 1-point charge that's multiplied by 1. This is the same thing. Potential is the energy that a charge of 1, a point charge, that's part, whatever they call it, a point charge possesses at a point. The energy that it possesses. But it's a property of a state, of a place. It's the same thing with the electric field. Calculate that point. So at this point, the potential is this much or that much. It's due to another charge. Because it's the electric field also.
Hey, look, a solid sphere. Solid sphere.
Go ahead. Just potential?
Yeah. No, yeah, that's potential.
I don't like those questions.
Fine.
Integral. Well, I know integrals anyway. It's easier not to mess up with integrals. Do you have anything else?
Nope. I haven't
Tried them?
I tried it, but I wanna know what I don't understand so I can
Do you have any questions? You can do them on the board then,
what?
if you want.
I suck.
Not a problem. If you want to. Not first.
I don't care. I think I'm gonna learn if I don't know it. I'm like on the board and I get it. Or we could do the homework that's due on the second.
Which one?
So.
No, I don't care. I want to work on, you're doing Gauss's stuff, right?
Yeah, we'll do the one that's due on the second. Or the one we did today, potentially.
I prefer that you
So that
try
we
it
both.
before.
Which one?
I mean, the homework. So if you want to do the homework
Yeah.
now, just do like work on each request on each one separately, and if you have a question on it, I can answer that. I'd rather not go over the homework before you try it. I mean, because look, if I keep on doing that, it's when you get to the exam, you're not gonna feel doing it.
Okay, that was one.
I haven't looked at any of these worksheet examples yet.
I might change the time for the Friday or something.
Totally.
I don't know because no one's showing up on Friday, obviously.
Oh, really?
Yeah, obviously no one shows up at 5 p.m. on Friday.
Wait, was I there last Friday?
Yeah.
Oh. I'm someone.
I want to be here on Friday.
Okay.
For the homework.
All right. I'll send out an email. Probably another Google if I'm gonna change it. So,
And just change that one day. That'll be a lot easier.
11 people filled out the Google anyway. Well, it's not like a lot of actions. It doesn't seem like it. I don't know. We'll see in future days if anything changes. I can't wait for Magnus.
I don't know.
When magnetism comes. I'm gonna show you how it was.
There's some. Oh, see. Okay. Wait, hold on. That's gotta be a surprise. So you can't see the price. Go. Wait. You breaking.
Trying to change the defaults.
Oh, alright.
What are you doing on this?
I don't know how to use this.
Hey, you just dropped.
Really?
Yeah, exactly.
See this? So I got most. They're pretty. She doesn't like roses though, so that sucks, but it's pretty.
Why is she surprised?
Okay. Well,
Later. Let's do this now.
I don't know what they are.
Things are. A equals 2.
10 centimeters or meters?
B?
L.
Or L. L equals 10 centimeters. 10 meters.
Alright, 4. What's that? Who's that? And we want to find EX.
At.
Hmm?
At.
At a point P. And that's about, this is the x-axis, and it's 30 degrees somewhere here.
Mm-hmm. It's 30 degrees from the x-axis at a distance 4, right?
Yeah.
From the top.
Gauss's law?
Yep. Draw your Gaussian surface first. Same way we drew it before. What's your Gaussian surface at your point? Where's your point? Where's the point P?
Here is B.
Right. Where's your Gaussian surface? You can change the thickness of the pen if that's annoying. This lines here.
Is it like that, the P?
P, yeah, it's at a positive 30 degrees from the x-axis at a distance 4 from the center. So yeah, pretty much, yeah.
P is here.
Right.
There's a Q over here.
Mm-hmm.
Plus 8, so it would be coming out.
What do you say?
The force in this one.
The field.
Yeah.
Yeah, it's plus 8, so the
So
field is pointing outward, right?
And that one outward.
Right.
And this one is negative 2Q, which would be coming in.
Negative 2Q, which would be true. Gaussian surface.
What?
Gaussian surface. First step, Gaussian surface.
That's what I'm doing.
Draw it first,
That's what I'm doing.
because you'll figure out that
On P?
Gaussian surface on P, right? What did we do before it? So if you want to find the electric field at point P, you draw a Gaussian surface. How? P has to be...
Oh, wait,
Yes.
like that.
Uh-huh.
Got it.
Right? What's Gauss's law?
On
the
this?
equation.
The equation for Gauss's law?
Should
Yeah, right.
I think
Uh-huh.
and that's
Q
Q
equals over epsilon naught. This tells you the electric field, or the flux, is proportional to the Q, to the charge enclosed inside the Gaussian surface. This is your Gaussian surface.
So
Is
it's
this charge
whatever is
enclosed?
only inside.
Yes, so you don't really need this. So that's why. This electric field, you don't need
I would have struggled with that too. So I just consider this one.
Mm-hmm.
Is there a second point?
And remember that this is a cylinder.
Or on the P.
No, yeah. Around the P, yeah, that's a cylinder, and the entire thing is a cylinder.
And this is just the point since the have the charge.
It's a cylinder, from the question.
Oh yeah.
Yeah, it's a cylinder. Inner cylinder, and there's an outer cylindrical shell, and your Gaussian surface is also a cylinder because symmetry. Remember symmetry thing? Has to be symmetrical, right? So if you
So
have,
I have to find the density along that cylinder.
yes. You don't have to. You can do it different ways, but let's assume you don't know that.
What is a different way? Oh, is it easier than
It's
that?
an easier way, yeah.
Okay.
You know Q codes.
You know, Kegel. Oh no, that way is not a legit way. I'm not gonna do it that way. What? It works on. It's not exactly right. I mean, it works out mathematically right, but it's not exactly right. Because anyway,
Just
so-
E equals
so because this is a cylinder, right? So I'll draw another dimension. This is what's here. This is your Gaussian surface. I just flipped it around, right? See what's happening here?
Yep.
Now, let's call it here. It's not going to matter really. But yeah, let's call it here. That's the point P, right? So, you're going to say that you can pick one of the three actually. So you can pick. We have three kinds of densities, right? Air density, or area density, or rho, which is volume density. Q over E. The other one is just small q equals over B equals small equals. Same thing with sigma q over big A, which is small q equals over small a. Over lambda equals to big Q over big L equals to small q over small L equals. You can use any one of these because in a cylinder, look what's going to happen. Try using anyone. Pick anyone and try using it. Take the first one, for example. And try using it. You can also use this. This one's easier. It's the easiest, sorry. This one's the easiest. But you can use it with anyone. Use that. Because
I
look why.
remember
Let me just show you
lambda.
why it cancels out. So I'll also leave this. So why it cancels out. Because if you want to find Q equals, you move this here, right? So that's Q. I'm sorry, Q equals. Q equals Q. V equals over big B. Q is given. V equals. This is your L that you're assuming.
And then times
This is the big L, which they gave you, right? So, this is your R. So that's Q times what's the volume of the cylinder? The volume of the cylinder?
4 pi. Is it 4 pi? 2
2 pi.
pi.
It's radius times the length. 2 pi. 2 pi times small L. Sorry, 2 pi R times small L. 2 pi R. 2 pi R. Which R? We're talking about.
This one, right? So it'll be this one.
We're talking about the turning volts.
The A. 2
Right. 2 pi A squared L over big V, which is this big V. So that's, sorry, without Q.
Why is it 2 pi a squared?
The big V is what?
Why is it 2 pi a squared?
2 pi A, sorry.
That's surface area, not volume, right?
No, pi A squared without the 2.
Yeah.
Pi A squared, as for volume, not sorry. I asked you something wrong. So 2 pi L over pi.
What
Volume of
happened?
the big one. No, we're just calculating the volume of the enclosed part. So we're calculating the volume of this thing. The volume of this. Pi A squared. The volume of the cylinder is the area of the base times its length, right? L is the length. Pi A squared is the volume of the base. So this is P pi times what's What's a big cylinder's volume? Big cylinder?
The longer one?
Yeah.
Be the same with the longer L.
A squared with a long L. These cancel out. This is the same as lambda. This is the same thing you get with using lambda. That's why you can use lambda. That's why you can use sigma. That's why you can use rho. And only in questions like this you can use three of them. Usually use
What is the most
what
common
makes more
case
sense.
of-
There's no common sense. There's no common most common. But there's one that's. I mean, what makes most sense? What makes most sense here is that you use rho because it's a volume. You end up with the same result. If it's a volume, you use rho. If it's just a sheet, you use the area, right? Which is sigma. Kind of the area. And if it's a wire with only one dimension or two dimensions, then it's it depends. Look,
Whatever I'm going to use, I'm going to...
if they tell you you have a sheet, an infinite sheet with Q equals, not an infinite sheet, that won't work. If you have a sheet with certain dimensions with Q equals 6 microcoulombs, which one would you use? Sheets. Which one of those would you use? Volume, area, or length?
Infinite sheet.
Yeah, sheets.
I have the length of the sheet.
You have the length of the sheet and you have the width of the sheet.
I don't know the area.
You have a line. Cylinder.
Last one?
Volume. Usually volume. Because you're talking about a cylinder. If they ask you a question with a cylinder and you want to find the Gaussian surface at a point inside, the last one won't work. You need to use volume.
Yeah.
Always look, if it's a body, volume. If it's a body in three dimensions.
I always think of the volume.
Yeah, volume. Use volume.
Because it's
Always use volume when it's a body. If it's a cylinder, use volume if it has only two dimensions, which is a sheet, use area. If it has one dimension, a line. Does the line have one dimension? Yeah. If it has one dimension, it's technically two dimensions. But yeah, if it's a line, you use length L.
I would use this
Even though, yeah.
yeah.
Use volume. Use volume, you get to the right answer. You'll get to the right answer if you use volume.
Sorry, I really suck at this.
No, it's fine.
Me too.
You're
I was doing the same thing last week. So.
We were doing this on Friday.
Basil, can you explain to me why this doesn't work?
Sorry. What?
Can you explain to me why this doesn't work?
What's going on there? Cube poles.
Does that work? Big only looking at
Is this two?
Oh.
Q over V times V.
Right. But do notations with the V's. Say which one is small of V, which one is big V. So you don't get messed up with this stuff.
It would be
This-
prime.
That's why if you get messed up here. It's big Q or big V. Small V or small V. So that tells you which so one Q equals. So it's small V, then big Q over big V. Right?
Say that again.
Small part you said it's small V. Over to small V, then big Q.
What do you mean by that?
As we said a second ago, we said rho is constant, right? Rho means anything.
Yeah.
So if you pick a big Q or a big V, that'll give you a small if you pick a big volume, it'll give you a big Q. If you pick a small volume, it'll give you a small Q. So you want to find Q closed. You use volume closed. So solve this. I'll get on this now. Solve this for Q enclosed. Q enclosed. Volume
Is that
enclosed.
just to know what you're looking at the picture, or is this what you're solving for? Because these are the same thing.
Yeah, but I'm just telling you which one, how to know which one is which, or what is what.
Oh, I just have this for density.
Okay,
And
so,
that
alright, so just, now which one is what?
for the density, so it would be this one would be that. This V is this.
Right. Mm-hmm.
And the big one would be that.
Right, small one.
I think you confused me.
Like that?
By this one.
Yeah, okay, no, I'm done. No, because, I don't know, some people like this better than other ones. I like this one.
That's the formula though, right?
Yeah, that's a formula, which is the same as that. This leads to that, and that leads to this. It's the same thing.
Okay. I'm slow. Sorry.
Mm-hmm.
Do you have an L pencil? Nope.
One of them. What'd you do? Where's your L2? Okay, you got the L2, right? Have L2, right? Right. Over I squared. L2 over L1. Is that a 1 or an L?
1.
Why? Where's your other L? Where's L1?
That's L.
Yeah, it's an L.
Okay, it was 1.
Oh yeah, it should be
Doesn't
now
cancel.
because you forgot the L. It doesn't cancel. Not yet, at least. Now put it back in Gus's equation, Gus's law.
It would be cancel as well.
It's up there. You can scroll up if you want. You can scroll up or down. You need more space.
Maybe over it's Q enclosed.
Right.
And that's it?
Right.
And you
Put
just
in
use
what
that
you
to
want.
solve.
But you still have the area. Did you solve for the area yet?
Within that area of. Okay. The area of.
Look back at Gauss's law. Where did A come from? Look back at Gauss's law, the original form. Where did A come from? It says that the electric field through the area of the Gaussian surface. The area of the
So
Gaussian
B
surface.
here.
Then. Right.
This imaginary surface.
Right. This imaginary surface. What's its area? What's its area?
And that's by R
Times L.
and L. How do you find L? You don't have L.
Let's see what
No, I
happens.
mean you have this L, but you don't have this imaginary one. You made it up.
Let's see what happens. You said a second ago that doesn't cancel out.
It doesn't.
Right.
Because.
But now you're dividing it over. You're dividing that over A, which also has an L term.
Oh, okay.
Yeah.
Okay.
Shouldn't she have a 4
Shouldn't she have a 4?
at the end there?
Professor would say.
Next to Q, L,
No.
because then 2a squared is the radius, so you should have 4a squared over a squared, and then you're left with 4 on top.
Oh no, be using the same radius. Okay. Yeah, because you're talking about volume. The volume. So, same as- saying this has this much charge in it.
Mhm.
And you're saying how much is enclosed inside the surface. It's still the same radius.
Can you take a picture of it?
I can send it to you. the radius is the same. Just let me save it. Did you do it?
I just get the 45 right.
Oh, you cancel out the wrong ones. No.
No, this is L2.
Yeah.
This is divided.
L2. This is L2 over. This should be L2. L2 over L, which means this is in the denominator. So that's like this is the same as multiplying times L2 over L. Right? L2, you said L2 was this thing. And no one. We call this one L. Right? This one is L.
I actually assumed this was L2.
Oh, did you? Why? Why?
Because L is
Q
value.
over B.
Okay, so that's
Big
the
Q over big B. So this should be the big L.
Yeah.
Using capital and small letter notations always gives you a little bit less confusion. This kind of stuff. That's why I like big L as well. But yeah, that's pretty much it. You just cancel out. And you end up with whatever you end up.
I don't think I got it.
What?
I had it twice now.
Yeah, I had it on Friday, now I don't have it. So, wait.
There's a lot of formulas. That's why he's lost.
You need guesses. That's it.
That's it.
For electric field?
I didn't think about row and stuff.
What?
Row and,
Yeah, roll on the. These are like, yeah. Well, yeah.
Is it mostly just you use E, like the integral of EDA, and then you have that equals to Q equals over epsilon, and then you do everything with that?
Yeah, integral. That's what you need for electric field. Let me just say this so I don't lose
What about
it.
the angle?
Export as PDF. Yeah. Yeah. Oh, okay. Yeah. How do you do the angle? Now, when did you find it? You find the electric field pointing this way, right?
Yeah.
That's what you just found.
Oh, so to find it along the x, it would just be cosine,
Cosine, yep.
and the opposite would be sine.
Mm-hmm.
That's it?
Yeah.
No kidding.
Cosine theta. Let me just save it. And what did one of you just ask?
Q enclosed you worried about in this problem was just based on length. So you had to figure out Q enclosed at like the smallest smidgen of length.
The Q enclosed you're worried about is just the length. Yeah. Let me just. Yeah.
And so you're looking basically at just one slice.
Session 2, 1 question. Session 1, week 2. Week 2, question 3. Okay. Yeah. Because you're always asking yourself, when you say Q enclosed, you're saying how much charge is enclosed in my Gaussian. So if you have a Gaussian surface that's bigger than this,
So if you're finding
that's the surface.
the line,
Because it's the surface. This is the closed.
but you
Closed
really
in
only
surface.
care about this.
Yeah, but it has to
one
be
point
enclosed in
P.
surface. Because you can't find the area of a line.
Right, I understand. You just have to consider that it's a surface.
Right.
And then you were finding P, and this is E, and E is the same everywhere. Because density.
Right.
Okay.
What if there were two in, and then you do the Gauss?
Two what?
Two charges.
Points or lines?
Lines.
Like here and here?
Yeah, and then Q is
Q is something and Q is something else. And you want to find a point P here. You want to find the electric field at point P here, for example.
yeah. I think I meant a circle, like a cylinder,
Like a cylinder and a
and
cylinder.
another cylinder, and then
Like
P
we had.
outside.
What if it was outside? Outside the problem. We just
Outside,
had.
the same problem, but outside.
Yeah.
Everything.
Like there are two inside.
I got it. Here.
He got it.
We have this, and we have this, and it's like that. And like that, and like that,
What do you mean?
and like that. Okay, so this is one charge. Let's just say that's little Q, and this is another like insulator, and that's big Q. And
You
you
feel
want
that's what you meant.
Yep, that's totally what you meant, because that's the
This is
exact
exactly
problem
what
we
I
just
mean.
had.
What is
Except
it?
it's the same problem we just had with an insulator, cylindrical shell, and then we only cared about this.
Right.
But what if the point was outside this?
Same thing, Gaussian surface.
Right.
Of 1 minus plus.
Do you just add the total charges together?
Yeah, after you find the
Q.
after you find Q enclosed, which is the amount of the charge enclosed. You still have to find.
Q equals
Q equals
density
Q
of
low,
this one.
So then you
And
would
that
have to do.
They would add up. That's all.
You would have to find the volume of this.
Right.
And then you would have to find, and then you take the volume of this, and then this minus this.
So if
No, not by volume like one.
Oh, I meant with.
Yeah, you find Q, the Q from each one.
Mhm.
By the
Q
same thing with the
enclosed,
row.
right?
Yeah.
I meant with negative, because one was negative and the other was positive. So if they were like, if you had a positive charge here, and you had a negative charge here, and then you found rho, and it was the absolute value of rho, and this was the absolute value of rho.
You can't
and then
subtract rows.
You can't subtract rows?
No, not in this case.
Why not?
Because they're not the same volume. They're not distributed over the same volume.
Right.
You have to subtract Q's. You can only subtract Q's automatically.
Okay. So you would do Q first?
You have to find the Q enclosed by each one.
Okay.
Which is the same thing. It's gonna be only dependent on L.
yeah.
Right. And then you subtract and add the Q's.
How do you do that? Is it Q1 plus or minus Q2 over epsilon? Okay.
No. It's Q enclosed. Yeah, it's Q enclosed over epsilon A. So if it's one of them ends up to being positive, so it's gonna be rho V. So rho 1 times V1, that's positive. And the other one's going to be, let's say negative. So that's rho 2, V2, negative. You add them together.
Over epsilon, and
Over
the
epsilon
area
naught.
would be this like.
The area would be, yeah, the area
The
would be
R.
like always a Gaussian surface. Gaussian surface there.
Gotcha.
One thing before on Gauss, if you do have something like this and you want to find the electric field at point P, you cannot take a surface like that because it's not symmetrical. I know what you said.
Oh, because it's a line.
Yeah, it has to be symmetrical. No, if it was just a line like this and you want to find the electric field at this P, you can take one here that's centered here. This makes it symmetrical. This makes the electric field go out the same direction. But in the second case, if you have something like this, this can't be a Gaussian surface because the electric field from here is going to be stronger than the electric field from here. So it's not going to be symmetrical throughout the entire thing. So if you try to write Gauss's law E dot GA, you can't cancel out the integral, you have to integrate it. If you can integrate it, do it. You're not going to be able to integrate it. So you can't do it like that. The way to do it, if they're not symmetrical, if it's a non-symmetrical charge distribution that you can get a Gaussian surface that works out, you do two Gaussian surfaces. So this is your point. And you want to do it with Gauss. This is your first Gaussian surface. This is your second Gaussian surface.
So
And the
two
result
E's.
from each one, 2E's,
Add or subtract.
depending on the direction.
Okay.
Depending on the direction. That's why they derive all the formulas, just to make all this process easier. Because
Yeah.
if you have a lot of stuff, if you have a lot of points, you're gonna have to take Gaussian surface for each one, and that's gonna be tedious. That's why you have KQ over R or R squared or 2K lambda over R in case of R and the other ones for the sheet. No problem. Did you write your email down so I can send it?
Kind of. It's PowerPoint